Science time. We're talking about today chemistry time, even ionic and metallic bonds. Let's start with metallic because it's easy for me to get carried away talking about ionic bonds, and if I have a time limit during that part, it'll be better than if I have a time limit in the metallic part. So we're going to talk about metallic bonds first. Bonding in general. Bonding occurs when? Fill in the blank for me. Bonding occurs, okay, during chemical reactions. Yes, very good. During chemical reactions, between what? Yep, between, we'll put substances because it can also be compounds. Between substances in order to, and that means why. Why do they do this? Yeah, I'll put achieve stability. In order to achieve stability. Regarding what? This achieve stability is talking about their mental health, yes? No. Talking about their valence electrons. Valence electrons. Specifically the Octet Rule, which applies to all the elements except for hydrogen and helium. In fact, if we think of the Octet Rule as all elements are more stable with 8 valence electrons except hydrogen and helium, which are more stable with 2, then the Octet Rule applies to all of them. So this is a truth of the universe. We had talked about an analogy before the video started where this can also, you can apply this to your interpersonal relationships, and that's fine. Maybe this will help you. Maybe you will be a better person after you learn this. But even if you're not, at least you'll know about bonding. So metallic bonding, can you guess just from the name what up with metallic bonding? Yeah, two or more metals bonded as what we call I love this, a sea of electrons. You remember this from physical science? Payne is trying to kind of stretch her analogy into the fishes in the sea about your interpersonal relationships. I don't know if I'm willing to take it, but the sea of electrons means what? What does that evoke the feeling of? What kind of verbs do you think of when you think of the sea? Motion, yes. So the electrons can probably move, which they can. What else can the electrons probably do? Not hunt for food, no. I was thinking flow. Peyton is very willing to use this analogy for, I don't even know what. Anyway, but what we have here in the sea of electrons is we have these kind of usually regularly placed. What we call it when atoms have a regular structure. That's what kind of atom? You remember? Not what kind of atom, but what kind of structure for a substance to have. You remember? Earth science people should remember. What do we call it when a substance has a regular atomic structure like this? And by regular, I mean like a pattern. We just did a lab about them today. A crystal, yeah. So this is a crystal, a regular repeating pattern of nuclei, and then what's in amongst the nuclei? These are kind of like islands, and the electrons are here like the sea. And just like the sea, they can flow easily. That's what's important about this, because what do we know about metals that would make this easy for us to remember? What do we know about metals that has to do with their flow of electrons?
They're solid.
Yes, okay, they're solid for one thing. Usually, not mercury. At room temperature, they're solid. They tend to be strong bonded. The state of matter a substance is in, a compound is in, is because of how strong the bonds are. So usually they're strongly bonded. What else is true about metals? What are some other properties metals have? Shiny. And they're shiny because this tends to form a flat surface. And so there can be reflections, and that's what we see as shininess. What else is true of metals? Strong. Their tensile strength does vary. What we call tensile strength is how easy it is for them to break. But that does depend on this, but it depends on another more basic property, which is what? If I hit this, what's going to happen? That's what I'm getting at, but I want you to say that again after I finish talking about this. If I hit this, here's my microscopic hammer. If I hit this, what's going to happen to it?
Nothing. It's
Nothing? It'll vibrate, but what I mean specifically is that if you hit a metal, say, okay, I have my, stand by. Yes, that's what I'm looking for, Mitch. Stop dropping everything. Okay, here, I have this. This is made of glass. This is made of glass. This is made of glass, which is, we'll find out in a second. This is, it depends, but it can be ionically or covalently bonded. But this is made out of glass. That's not metallically bonded. But if I had another one that was metal, and I hit both with a hammer, if I smash both of them on the floor, and what's going to happen to the metal one? It'll dent, and this one will probably shatter. And the reason for that is that I'm going to remember this, but when I hit this with my hammer, all these atoms are going to shift somewhere else. But they're all going to shift somewhere else, but because of the sea of electrons, they're still fine. You know, they're still just as bonded to the new ones they're next to as they were to the old ones. Do you see what I mean? And this is called what? What property is this? Malleability, which was one of your vocab words. Malleability is the ability to be hammered into different shapes. And it relates also to ductility, which is the ability to be drawn out into wires. And metals exhibit both of those properties. And then the ultimate property of metals, the final property of metals that we're going to talk about because of the sea of electrons is what? You say they're good conductors of heat and electricity. So if we have an electrical charge over here, it's easy for the electrons to move, and so they can, since they're electrons, they'll be attracted to that, this positive charge. If there's a electrical charge over here, it's easy for them to move, and so we end up with a flow of electrons. And we call the flow of electrons what? Yeah, electric current. Electrically conductive. What's the most electrically conductive metal? Or most electrically conductive element?
Was I right?
I want you to mention that, though. What did you say? She says copper. That's not technically right. It is what we use in wires. So why would we not use the most electrically conductive?
So not shock waves.
No, that's not true. No? What is the most electrically conductive? Does anyone know? No?
Iron?
No. It's silver. So why would we not use silver? There we go, because it's expensive. Copper is quite a bit cheaper than silver. I don't actually know if this is true or not, but a lot of times in my lessons... No, it ain't. Thanks for your concern, Mitch. I wonder if the mic picked that up. Your terror that my kettle might fall down. Anyway, I don't know if this is true or not, but a lot of times I say that if I were in charge of something like NASA, and what I really was worried about is the flow of electricity, I would use silver wires because cost is not an object, you know, in a capacity like that, and you want to be sure that the electrical current can flow. And maybe there's different reasons why that isn't the case. But silver is a better conductor of electricity and heat. Do you have questions about metallic bonding? We will do a little demonstration about this to show a thing called alloying. And alloying is just a special kind of chemical bonding where, this was one of your vocab words, but two or more metals bond. So what are some alloys? An alloy, obviously, if alloying, a verb, is what happens when that bonds, what would be an alloy? It's a substance where it's really actually a mixture. Yeah, it's two metals bonded together. It's a mixture of metals. But like steel would be an alloy. Steel, because in this case, steel is iron and carbon, which carbon is a non-metal, so that's not the best example, but it is behaving as a metal in that case. Another example would be bronze, which is copper and tin, or brass, which is copper and zinc, or my favorite one, my absolute favorite one, is electrum, which is an alloy of silver and gold, which I think is beautiful. I just told my wife the other day that her hair is the color of electrum, which is just one of the dorkiest things you can say. Don't use that as a pickup line, unless you're at like a dork convention or something, or an alloy convention. And you're like, hey baby, you got that electrum hair? And she's like, yeah, I have a PhD, and that's why I'm at the alloy convention. Okay, let's move on to, you have questions? Erase this, get that trash out of here. Do you have questions about metallic bonding before we move on to ionic bonding? I'm going really fast because I need to get through this, and I want you to have the information you need to do a good job. We will, just so that you know, we will have, after we finish the video, we will have a practice worksheet for you to do what we're about to do.
Just don't waste it.
Alloying. So now, right, and where I had written before metallic bonding, where I had written before metallic bonding, please write ionic bonding. And we said that metallic bonding occurred when two or more metals bond together. That's true. What might be occurring when, or what might be combining when ionic bonding occurs? A metal and a, yeah, we don't call them regular elements usually. We call them Lily, non-metal. Yeah, ionic bonding. Ionic bonding involves a metal cation and a non-metal anion. Yep, K-A-T-I-O-N. What charge then would a metal cation have? Do you know? You should know because it was in your vocab. You should know from physical science. You should know because of where the metals are on the periodic table. What kind of charge? Yeah, they have a positive charge. A cation, which is a metal, has a positive charge. An anion then has a negative charge, which is that of a nonmetal. What has happened with the electrons of a nonmetal that makes it so it now has a negative charge? What has it done with those electrons? It has gained electrons. Just let that sink in for a second because that's something a lot of people get confused about. What happens to the charge when you gain more electrons? It decreases. You have a negative charge now because electrons themselves have a negative charge. So if you are gaining electrons, if you're an atom and you gain an electron, you now have a negative charge. Okay. A way I remember these is a cation is like a little cat, and it's positive and happy. I don't like cats, but this is a good way to remember it. Cation, positive, happy little cat. Anion is like an onion, stinky, bad onion. And I do like onions, so don't remember it that I like and dislike things. But cat, happy, positive, onion, bad, negative. Okay? And there's no moral or ethical connotation with cations and anions. I'm just saying, obviously there's a connotation with negative and positive, where if I say I had a negative day, I mean bad. And so you can remember them that way. You don't have to remember them that way, but that's a way you can remember them. Do you, whatever. Okay, this bonding that happens when what occurs? We had said already that bonding in general happens to achieve stability. So if we have a non-metal, we'll just pick a non-metal real quick so I can draw it. Okay. Phosphorus. That's one we just watched. Good. How many valence electrons does phosphorus have?
7, 6, 5, 8, 7, 6, 5.
Is it 6 without me looking?
It's not 6, no. It's 5. It has 5 valence electrons.
You said 6, 7, 5, 9, 12.
Okay, now pick a metal.
Iron.
Okay. Which iron cation? Iron has 2 cations, 2 and 3, I think. Yeah, 2 and 3. So which one do you want? 2. So it has 2 valence electrons. And in fact, it always has 2 valence electrons, but it has 2 different oxidation states. I wish you hadn't picked iron, but that's fine. 2 valence electrons. We'll just say it's 2 and it has a 2 plus charge. This has a 2. Oh, sorry. Let's not write that yet. Can the iron and the phosphorus bond together?
Yes.
Yeah, well, what must happen for that to occur?
It must react.
Okay, there will be a reaction, yes. But what has to happen?
Share the electrons.
Which one gains electrons? Phosphorus gains electrons from where? The iron. The iron doesn't want these two. In order to achieve stability, the iron's going to get rid of 2. We are going to need to have some wild combination. I wish you had picked a different. Let's pretend that instead of phosphorus, you picked sulfur. Great. I'm glad you picked sulfur. There we go. That'll just make it easier. So now, the iron has lost 2 electrons. What's its charge now? Yep, positive 2. The sulfur has gained 2 electrons. What's its charge now? Negative 2. And then they're both happy. They both go on their merry ways, right? This one has got what it needs. This one got rid of what it needs to get rid of. And they both just leave. Is that right? You can tell from the way I'm phrasing it that it's not right. What does happen? Yeah, they're stuck. Why? What force sticks them together? Yeah. No, they're not being shared. In this case, they are. This one has given something to this one. This one completely. So, yeah, no, this is not the ideal way for a relationship to be. Great. He would get out of here if he could. He gave what he needed to give, and I shouldn't use these pronouns, but what's holding them together? The bond of holy matrimony. Now, what's holding them together? The electromagnetic force. Why? Because what? Because what we just did. This one has a positive charge. This one has a negative charge. They're attracted for the same reason that protons and electrons are attracted. They're held together by the electromagnetic force, and we call that an ionic bond. Just to be clear, they did not share. They are not sharing. The iron gave 2 electrons to the sulfur, which received 2 electrons. Now the sulfur would have how many altogether? I'm going to do these in a different color. How many does the sulfur have altogether now? No, it had 6 before. How many does it have now? Now it has 8. Wait, what does that match now? Yeah, it has the same as argon, which means it has satisfied its octet rule. And how many does iron have now? It has 0 valence electrons, but how many does it have in the next layer down? Well, we go back. It has the same as argon now. They don't have to have the same as argon, but it does have the same configuration as a noble gas. Good? They're both more stable than they were before, and they're both held together by the electromagnetic force. So how do we name this thing? Well, we shouldn't have started with iron, but let me tell you, we're going to give some rules for ionic naming. Here are the rules. We always name the cation first, and then the anion with the suffix changed to, does anyone remember? No? Ide, yeah. IDE. So for instance, if we had sodium and chlorine bonding together, what would that make? Sodium chloride, which is table salt.
Oh yeah, we actually did a thing like this.
Sodium chloride. That's it for naming, really. It gets more complicated with the transition metals, but that's the basis of the naming, is that we just put the cation first, and then we have the anion second, and we change the ending to ide. And then to write formulas, ionic formulas, we have the cation first, then the anion, and then we change the subscripts. So charges add to what? What must the charges add up to? Well, what do they add up to in this example? What's 2 minus 2? Yeah, 0. So they add to 0. Let's do an example of that. I'll leave the rule there and we'll do another example. So on this worksheet, you'll either be given a name and you'll have to find the formula, or you'll be given a formula and you have to find the name. Good? Let's do this one. This should be pretty easy. What's the name of this? The cation. We have to name the cation first. Which one here is the cation? Well, first one, because we had to, in the formula, we put the cation first. So it's potassium fluoride. Yep. And that's it. That's all you have to do. It gets a little bit more complicated, but that's pretty much all the worksheet is. Now what if I had, let me do this one. What if I had calcium chloride? Well, what do I do first? Write down? Write down what? Calcium symbol, which is? Ca, and then I write down chloride. It's chlorines, which is Cl. But is that good enough? No, I have to make sure their charges add to 0. So what's the charge on the calcium? How do I know? Charges add to 0. What's the charge on the calcium? Nope.
No
Positive 2. How did Mitch knew that? Because he's magic?
Yes.
Yeah, no. How did Mitch know that? How many valence electrons does it have? It has 2 valence electrons, and so when it bonds, it must lose 2 valence electrons. So it must have a charge of positive 2. So calcium's is positive 2. What's chlorine's, or what's the chloride's ion's charge? Negative 1. So do those add up to 0? No. So I need to do what with the chloride? I can only ever multiply. What do I need to multiply chloride by? I multiply chlorine by 2, and I use a subscript. So I change the subscripts so the charges add to 0. What's the charge of the calcium again? I sometimes put the charges above it, or I don't. But if you're working on it, you can put the charges above it. The charge for the calcium is 2 plus. The charge for the chlorine is -1 or 1 minus, or just minus. And then we put subscripts that multiply. What do the subscripts do? What mathematical operation does subscripts do? Multiply, always, by the charge. So what's our total charge here? 2 plus 2 minus is 0. 2 ways to complicate this. You want some ways to complicate it, Mitch, so that it can be harder? Okay, here's 2 ways to complicate it. Ready? First way, polyatomic ions. Hey, wait a second. You know about polyatomic ions, right? Right? You know all of them, right? You know all of them, right? So what if I had the name potassium nitrate? Not nitride, nitrate. Is there a polyatomic ion named nitrate? Yes. So what's potassium, first of all? K. And what's nitrate? NO3. Okay. What's the charge? What's the charge on the nitrate? You have to have that memorized too. What's the charge on it? Minus. What's the charge on the potassium? Positive 1. So do they add to 0? Yes. Yeah, so they already do. So that one's done. It's just KNO3. What if we have no, give me a second here, Mitch. Calcium. No, I'm going to use magnesium. Magnesium hydroxide. First of all, you have to be able to tell if the name includes a polyatomic ion. How do I know that this is a polyatomic ion and not just an element or a monomer? Because it doesn't end in "ide." The polyatomic ions end at "ate" or "ite," except hydroxide and cyanide, right? Those ones are kind of exceptions. So magnesium hydroxide, how do I name that? Mg. And then what's hydroxide? What's hydroxide, babies?
H. No.
What's hydroxide, babies? Camden, what's hydroxide?
Here, I'll tell you.
Why does no one know what hydroxide is, Mitch?
Is it NH?
No, hydroxide. There's no N's in it.
Hydroxide is
It's one of the first ones you memorized.
OH-1.
OH. What's its charge?
Actually, -1.
Okay, the charge on hydroxide is -1. What's the charge on the magnesium?
+2.
Nope, +2. So how am I going to have to make this so that you have to multiply it by 2? But listen, here, look at me. The kicker is, if you're multiplying polyatomic ions, that has to go in parentheses. Okay? It has to go in parentheses because that kind of distributes it like in math. So if we had, and look, the 3 here in nitrate was part of it. So if instead of potassium nitrate, if we had calcium nitrate, we would have had to put the parentheses around the whole NO3 and put a 2 outside of it. Okay? And we will work on these. I just want to get it on video so you can have these examples. Can you do this in the reverse? Well, they're still super easy to name. If you have the formula, you just say calcium nitrate. Okay? Just so you know, these ones back here where they were just 2 elements are called binary. Bi meaning 2. And these ones are called complex or polyatomic ions. And then last way to complicate it. Here's a new way to complicate things, Mitch. You love this. If we use transition metals, except for silver and zinc and aluminum, but we're going to talk about those. But if we have transition metals, the names must include oxidation state or charge in parentheses after the metal. Can the camera see what I'm doing? Yeah, pretty much, or at least as good as it usually can. The names must include the charge, and why might that be? What do you notice about, on the periodic table, look here, you can see the charge. Potassium is 1. What's chlorine? -1. Well, all these ones in the middle, the transition metals, what do you notice about them? Well, their oxidation states, they can have gajillions of oxidation states. And so in order to tell which one is which, we have to put the charge. So look, if we have this, FeO, versus this one, Fe2O3, well, these are both iron oxide. So how do we tell They're completely different things. This one's rust, and this one's like the bluing on the rifle barrel. They're completely different substances, so how do we name them differently? Well, all we do is put the charge in parentheses after the name. So this one is iron 2 oxide, and this one is iron 3 oxide. And how do you know? I hear Lily mouthing it. How do you know? How do I know this one's iron 2? Well, what's the charge on oxygen always? -2. So if this is -2 and they have to add to 0, what must this one be? +2, so that goes here. If this one's -2, but there are 3 of them, what's that total charge? -6, and there are 2 iron, so that must be, each one is +3. So we call it iron 3 oxide. Do you see? Okay, and this is all fast. We will do more practice with this, but this is all the information you need on a very basic level. You just need practice now. Do you have questions about this before we dismiss you? Before you have to do 7.5 pages of worksheets? Yes? Oh, it's more like 9, actually. Questions?